In this session I'll give you 4 examples from the text that illustrate the use of the first isomorphism theorem, which I've summarized here in a rectangle in very compact form. Basically it's saying you start with a homomorphic function mapping between 2 groups, f, that's your function, and there's an isomorphism between the group that you start with. You form from your function f, you find the kernel k, and then with that kernel and your original group big G, you find the quotient group, factor group, and that factor group, its members, which are cosets, will map 1 to 1. There'll be an isomorphic mapping between the cosets of this quotient group and the members, the elements of the image set. You know, all possible mapped to values of f of some member of this, you know, f of some coset in effect. So there's the first isomorphism theorem in very shorthand form. So just put it up there for reference. Okay, before I get into the nitty-gritty of these 4 examples, let me say a little bit about what the 4 of them have in common. So it's almost like a mantra. We're doing the same thing 4 times. So what are those things? Well, you look at the mapping that you're given in the 4 cases, 4 examples. Show that mapping is homomorphic, because that's important. Okay. Then find the kernel and find the image of f. Right. And then once you know the kernel, you can write down this first isomorphism theorem in this form. Once you know what the image of f is, and once you know what the kernel is, you can and you know what G is. That's given when you start the problem, right? So you can write down something of this form, like, and I've put a rectangle around the, oops, I should. Right? So, you know, your big G, your kernel, and your image of f in the same form. Dum, 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 dum. Right? So we will just go through that process 4 times. Illustrate the use of this first isomorphism theorem in this form. Okay, so let's start. So you're given a mapping. You're given a group G, big G, and maps to some other group H. So in this case, we're mapping. Let's see, what are we doing? We're mapping the integers to a set of residue classes. Okay. What is Zn? Well, it's written it out here. It'll be of order n. Right? So you have n different residue classes. For example, each of these residue classes is an infinite set. Right? This one here, for example, it's shorthand, so square brackets 0 mod n, little n here, integer n. What does it mean? It's a bit of revision here. It's the set of all integers that are, what's the word? Congruent to 0, mod n. In other words, 0, plus minus n, plus minus 2n, plus minus 3n, and so on. And this residue class, it's again an infinite set of integers. It consists of all those integers that are congruent to 1 mod n. So that set would contain the numbers, the integers 1, 1 plus or minus n, 1 plus or minus 2n, and so on. Right? And you have n of them. Okay, so you're mapping an integer into one of the elements of this this class, this set. Yeah? So you take an integer and you'll map it into one of these. So of this form. And here's your mapping in terms of elements. So you take this integer m belonging to z here, and you map that with f into a residue class. Right? And the residue class is m mod n. Okay, so that's your mapping. All right. So go through the recipe. How to show that f is homomorphic? Well, the binary operator here is plus in both cases. So fn, the times, the binary operation here won't be a multiplication, or well, it's just addition, right? So we're trying to show that fm1, fm2 is the same as f of m1 plus mn, or fm1, m2. Okay, so start here, and what is this? Well, we just use this by definition, so m1, so it'll be the residue class m1 mod n, similarly here, but just from ordinary rules of residue classes behave like integers, remember? So you just add these two, get a, so within the residue class in a sense, okay? But that, using this definition, is just this. So this equals this. So therefore f is homomorphic. Alright, if it's homomorphic, then it will have a kernel. Right? The subset of integers, subset of big G here, that map to the unit of H, your target group. Now what is the unit of this? Well, it's this one. Right? It's the residue class 0 mod n. That is your unit of this this group. All right. Now, what elements in G map to this unit? Well, can you see that they will be the elements 0, plus or minus n, plus or minus 2n, plus or minus 3n, and so on. So can you see that you put all those in a set, and remember that set, and they all map to the unit of your H, which is this one here. That set, the kernel, in fact, can you see it's just n of z? It's just the multiples of n. So it'll just be nz. So your kernel is nz, right? So we know what this is. Now next we need to find out what the image of f is. So how to do that? So we've found the kernel here. It's just nz. It's all the multiples of n, little n. Okay, what's the image of f? This mapping. Well, it's the set of all possible f's. I mean, mapped. It's the set of all possible mapped to values, right? So it's all possible members that map to this, which are what? Wait a minute, sorry. It's all So what are all possible members? Well, you can have anything here within a range. M here can take it within a range of 0 up to n minus 1. Okay? So you could have a 0 here, 1, 2, up to n minus 1. So these residue classes here, they're all possible values that you could have. There's no point going above m. There's no point going above n minus 1, because if you do, it just gets absorbed in the residue class. So the possible values that this can take are these. Right? So the set of those, well, effectively that's just Zn. Right? That's what Zn is by definition. These are all possible values that this can take. So so your image, all possible different values for f, which that's what the image is by definition, okay, is just Zn. Right? So we know what the image is now. We know what that is. We know what the kernel is. So we can use this theorem now. We can use the first isomorphism theorem and just write down the left-hand side is isomorphic to the right-hand